Well, hello and welcome again into our journey into algebra and number theory, and this is the second video in the section on the integers, where we're trying to look at number theory from an algebraic perspective and learn a bit of abstract algebra in the process of learning some number theory. So we're up to the idea of multiples and common factors, which is a basic idea that you've seen back in high school, but we're going to try and look at this in a slightly more abstract way. So we take any integer and we're going to define nz to be this set of multiples of that integer. Now, of course, n could be 0, in which case this is just a single element 0, but for any non-zero element this is going to give us the multiples of this. Now we're going to define the LCM, the lowest common multiple, of two integers n and m to be the smallest positive element in nz intersected with mz. It's a slightly more abstract definition than what you might get in junior high school. We're going to denote this also by square brackets nm. And similarly, the greatest common divisor, the GCD of n and m, is the largest positive integer which divides both n and m, which is our usual definition. So just as example, if I take n to be 4 and m to be 6, then I take 4z, so that's all the multiples of integer multiples of 4, intersect all the integer multiples of 6, and of course that's going to give me, if you compare these two sets and take their intersection, you see that you get all the multiples of 12, which I can write as 12z. So the LCM of 4 and 6 then is the smallest positive integer in this set, which of course is 12. Another way of writing this is square brackets 4, 6 is 12. Similarly, you can check the LCM of 2 and 5 is 10, as you would expect, and of 15 and 25 is 75, as you would expect. Now we can also define this in terms of the prime factorization. So if we take the unique prime factorization of n into a product of primes, and we take m to be its product of primes. Now notice this is slightly different to the usual, and we're going to have the same primes in both lists. So some of these alpha i's might be 0, and some of the beta i's might be 0. So alpha and I and beta I are non-negative. So it's slightly different to the usual unique factorization. We're going to include primes that are not actually there by taking a 0 index, so we have the same primes in both factorizations. And then the LCM of these two numbers, if you think about it, is just going to be the product of the prime powers, where we take the maximum of the alpha I and beta I all the way through. So there's another way of defining the LCM. Now the greatest common divisor then is of two integers is the largest positive integer which divides both of these, and we use the notation GCD of n and m, or sometimes we just write round brackets n and m, which is a bit easier. So often we'll just leave out the word GCD. So the GCD of 12 and 32, for example, is 4. It's fairly obvious. That's the largest integer that goes into both. And it's easy to see then that if n and m are in factored form, as we did up here, then the GCD of n and m, you take all of those primes and you raise it to the minimum of the alpha I and beta I all the way through. And having got that, then we can now state this lovely connection between the GCD and the LCM, and that is, if you multiply the LCM times the GCD, you just get the product of the numbers. We take absolute value in the case that one of these is negative. And proof of this is just an exercise. So you can in fact the easiest way of doing this is to use our definitions up here, or these results up here, and you'll see this comes out quite easily. Now if the GCD of m and n is 1, we say that m and n are relatively prime or co-prime numbers. And what we'd like to do now is to try and abstract this a little bit and look at the GCD of two numbers in a slightly more abstract way. And to do that, we're going to introduce this notion of an ideal. So we've already seen, for example, this set 5z, which is the multiples of 5. We've already seen that this is a ring. It's closed under addition, subtraction, multiplication, and it has a 0 there, and it obeys the associative laws and commutative laws and so on. So we can think of 5z then as being a ring inside the larger ring of integers. So we can think of this 5z as being a ring inside a bigger ring, the ring of integers, and we're going to call such a thing a subring. So 5z is a subring of z, but 5z actually has more properties than this. It's got the following properties. It's closed under addition, subtraction, multiplication. Well, that's because it's a subring. 0 belongs to the set. Well, that's okay. But the interesting thing is that if we multiply any element of 5z by any integer, not just integers inside 5z itself, but any integers, then the result remains inside 5z. So if I pick a number like 7, multiply everything, or pick any element here and multiply it by 7, say 5 for example, 35, and that still belongs to this set. Now subrings of a given ring which have these properties, in particular the third one's very important, are called ideals. These are called ideals. And a little picture just to describe what's going on here. So here's our ring, and then we have an ideal which is inside, so it's a subset. And if we pick two objects in this subset and add them, we stay inside there. We subtract them, we stay inside there. We can multiply them together. So I can put AB here as well. That stays inside the set. But also, if I take any x which is outside of the ideal, but I multiply it by anything inside the ideal, then I stay inside the set. So this is closed under external multiplication from within the ring. Now the formal definition of what we mean by an ideal is here. So we take a non-empty subset I of a ring R is called an ideal in R if, for any two elements A and B in the ideal and x in the ring, the sum and difference of the two belongs to the ideal, and any multiple x times that belongs to the ideal. That is why we didn't technically need to have the AB here, because I could simply take these two. If it's closed under exterior multiplication, well, it's closed under automatically interior multiplication, so we have that one there. So notice in fact that if x is 0, we have 0 belongs to the ideal by rule number 2. So ideals always contain 0. Now, as you might guess, we got this by generalizing this set, and so as you might guess then that nz, where n is an integer, is always an ideal. Well, we can get more complicated ideals. For example, if I take this set, which consists of all integer linear combinations of 5 and 7, so I take 5x plus 7y for any x and y in z, then this is an ideal in z. Again, we just check by a little proof of this. If we take any two elements there, a and b, in this set S, then by definition A has to be some integer linear combination of 5 and 7, and B has to be some other integer linear combination, and if we add or subtract we get this, which of course is also in S. And if we take any integer n and multiply something in the set by n, then we simply again still have an integer linear combination of 5 and 7, so that's also in the set. This one is example, you might have a look at this one here. This is also an ideal. It's all the integer linear combinations of 6 and 15. That's also an ideal. Now notice that in this set S here, 1 belongs to S, because I can build 1 by taking 5 times 3 plus 7 times minus 2. And once you've got 1 in the set and it's closed under exterior multiplication, then you can multiply this by any integer and you're still in the set. So this set in fact is just equal to the whole set of integers. On the other hand, this set T, if you play around with this, if you write this out, you'll see that T consists of this set, and this is just all the multiples of 3. And I'm going to write that as these angle brackets 3. It means the set generated by 3. That means all the integer multiples of 3. Now, as you where we're headed for here, of course, is the fact that the greatest common divisor of 6 and 15 is 3, and that turned out to be the so-called generator of the ideal. So any ideal in a ring R, which can be expressed in this form, so if you've got an ideal in a ring and you can write it as a multiple of one object, as we did here, then that's called a principal ideal. And a ring in which every ideal is principal is called a principal ideal domain, or PID for short. In the integers, we'll see that all ideals are principal, but to get to that point we need the so-called fundamental division algorithm, which is the basis of pretty well all of number theory. And we'll continue that in the next video.